Um, so we'll start. We're going to go over to SPSS and we're going to go analyze dimension reduction factor. So I've got the data set open, analyze dimension reduction factor, and you pull over the 13 CS items. So part 2, I sent those over. Part 3, we're going to kind of go down each of these and select what you need to. So descriptives, you want to check univariate and initial solution. So descriptives, univariate, initial solution. Next, we're going to go to select extraction, and we want to check unrotated factor and scree plot. So unrotated scree plot. We want eigenvalues greater than 1, that's a default, and then we're going to select our method. Many of these are similar, but the one that I prefer is principal axis factoring, and that's based on DeVellis' suggestion. Corresponds to determining a latent construct. And then we're going to select a rotation method that allows the subscales to be correlated with each other. So rotation, method, Promax or direct Obermann are both correlated. Rotations, and this is a default. And then under options, if we didn't do something more sophisticated, replace with the mean is better than the others. And I like to sort it by size. That's sorting the factor matrix by size, and I suppress less than 0.20. Our criterion is we want above 0.50 loadings and cross loadings less than 0.25. But if there's something that's right on the cusp, I want to be able to kind of see that. But stuff that's well below, I'm not worried about. So that's this one. And we're going to hit paste. That saves our syntax as opposed to actually running it. And that lets us put things back together later. So I've already put the syntax together, so I'm not going to hit it now. Okay, so I'm going to run this initial set on all the items. And you can go through and kind of look at the means. You'll see that there are a few where the means are particularly low. And this is telling us that it extracted 2 factors with eigenvalues above 1. 6% of the variance, and the second is 15. 66%. This is the scree plot. So what you're looking for here is where there's a pretty discrete bend. So after the second factor, all the other factors are kind of a wash. They're explaining a similar amount of variance. And you go down to the pattern matrix where it's been rotated. And what I make of this, so it's, these are in order of the strength of the loading. So we've got a strong first factor, and then we have a few items that could potentially make up a second factor. This one doesn't quite meet our criteria, but I mean it's pretty close. So if we wanted to, we could try to end up with a 2-factor scale, and it looks like we'd end up with the negatively valenced items kind of being on its own factor. Or for this round, I'm going to just assume that we don't have quite enough items and these are not adding that much, and so I'm going to drop these off as well as this one that's cross-loading. So I'm going to drop 6 10, 9, and 11. This gives us the correlation between those factors. So that's what I did here. I'm going to run that. You can do something similar. Go through and look at descriptives on the items. We have a single factor now. It's explaining 70-ish% of the variance in the remaining items. And all of our loadings meet our inclusion criteria. So this would be a place to stop on our EFA. And then, so the answer here would be we initially had 2. We dropped, what did we say? 6, 9, 10, and 11. And then we repeated it. One factor, all met inclusion criteria. So we'd be done, and then we could calculate the alpha on the scale. So initially, the alpha was 0.93, and if we had kept this item, we would have probably reverse coded it, but we didn't keep that one. So that would probably be a little higher. What I'm doing is I'm looking at the item-item correlations, and we can also look at the item total correlations. And then if we run our alpha on the final set, we get alpha 0.96. This would probably tell us that if we wanted to, we could probably reduce the scale some, because do we really need 9 items to assess this construct? Potentially we could reduce the length of the scale and still have an alpha around 0.90. So what I'm going to do in the second phase is I'm going to run a CFA on the same sample. So that's definitely overfit, but I want to see if we've got some indications of poor fit, particularly the RMSEA, which picks up on redundancy in items. It has a penalty for that. And we may be able to make some additional changes based on those results before we try to replicate in a different sample.